Hello students, in this set of videos we're going to be looking at cumulative distribution functions for discrete and continuous distributions. Before we do that, let's go back and look over some of the stuff from our core content in the HL class. So we started by looking at discrete random distributions, and for a discrete random distribution we looked at all of the possible values that x could take and the probability of that happening. So this would be for summing the total on two dice. So this was discrete, where we can take on discrete values. Continuous is where we looked at the probability density. So with a continuous function, because it's continuous, we're looking at all possibilities of x, where x can go on infinitely. And so, let me come down to continuous. So we're looking at, with continuous, all values of x from negative infinity to infinity. So taking an individual probability doesn't make sense, because since there's infinite choices, the odds of it picking one exact x for it to take on, the probability would be 0, because there's just so many different choices. So when we look at our y-axis here, what we're really looking at is, so this y-axis is probability density. It's not probability itself. So our f of x value is the probability density. Typically we talk about a value of x landing between a range, so from A to B, say, and then our probability is the area, because if I have probability density, well, that's probability divided by x value. So when I find area with my length and width, then I end up with just the probability. So that's why when I say the probability from A to B is the integral from A to B of f of x dx. So let's go back into our notes here. So we want to define probability distribution functions, and so we can think of having a probability density function. So which is always positive. And when I sketch it, I'm looking at going for all values of x, but at some point, typically I define my f of x to be 0 for some values of x less than a, let's say. And then maybe it's going to have some sort of function for x that's between a and b. And then it'll go back to being 0 for values greater than b. So it'll be a picture similar to something that I just showed. We know that our f of x has to be greater than 0. We also know that the integral from negative infinity to infinity of f of x dx is going to be 1, because the probability that x lies between two values, so let's pick c and d now, is going to be the integral from c to d of f of x dx. So we talk about probabilities here. We talk about x being between a range, not a single value. Okay. The other thing now that we want to talk about that's in our syllabus is the idea of the cumulative distribution function. So normally in our calculator cumulative, we have our CDF when we think about our different distributions on our calculator. So a cumulative distribution function is capital F of x is how we denote it. And it's the probability that x is less than or equal to, it doesn't actually matter, some certain value x. So here in my notation, this is a capital X, and this is lowercase x for some individual value. With my continuous probability distribution function, that's going to be the integral from -infinity to x of my f of x dx. And so I could say that f of x is the derivative of capital F of x, vice versa. So there's not an equal sign here. There's an implication here. All right, like we saw with the main unit in the HL's class, expected value is going to be my mean, and I'm going to find the mean by integrating x times f of x. And this goes back to the idea with a discrete distribution that if I want to find expected value, I take the sum of probabilities times the given x value. So the integral of my f of x is giving me the probabilities, multiply it by the x to get the expected value. I can calculate variance, which is of course standard deviation squared, by calculating integral of x minus mean squared, f of x dx. If I expand this, I get expected value of x minus mu squared. This becomes integral x squared f of x dx minus mu squared, or expected value of x squared minus mu squared. Sorry, this is parentheses in the wrong place because this is expected value squared. This is expected value of x squared. So these are some formulas we need to know. A lot of this is in the formula booklet, but we need to know this vocabulary for a cumulative distribution function. This is my CDF notation typically. And again, less than or equal to doesn't matter for continuous distributions. It matters for discrete, but not continuous.